We haven't actually started recording yet. I'm waiting.
There we go.
There we go. All right. So welcome everyone to the July edition of the Big Rig meeting, which I particularly like the name of. If you're interested, it's the Research Interest Group. I'm Langdon White, and I will be your host today for reasons. However, we have a fun agenda. First up, we're going to have one of our interns presenting on, I assume, what they're working on. But I don't actually have a title for your talk, Ryan. But we'll get to that in a minute. Then we're going to do part 3 of the paper reading group with Ahmed. And then we're going to talk about what's called the engineer in residence at the end. We are looking for a hard stop today because at least some of us probably have big, org-wide meetings at 4 o'clock. So I'll probably be trying to keep people on time. So Ryan, do you want to go ahead and get started? Oh, sorry. Actually, before you do that, let me just ask, are there any questions? Anybody who have any announcements or anything like that that they want the opportunity to bring up?
I was just going to say, I'll sort of introduce, I guess probably everybody knows Ryan anyways, or a lot of people do, but he's one of the interns we hired out of Boston University, out of the EC 440 operating system class that either myself and Oren or myself and Manuel taught, which actually you weren't in my class, right? Anyways, I think you were a TA in the class I was teaching, but you... were you in there with Manuel?
Yes.
Yep. So I've taught with Manuel a couple of times too, but I was not one of the active teachers when Ryan was in there. But he's done really good work, and so we have a couple of projects that he's working on, and just give him let him give an update on a couple of projects. Go ahead, Ryan.
Awesome. Thank you. So let me just share my screen, and yes, here we go. So hello everybody, my name is Ryan Sullivan. Thank you for the wonderful introduction. And yeah, these are just the 2 projects that I've been working on with Dr. Woodman, and I'd just like to give a quick little update on it. Or Larry. Yeah.
I'm no doctor, but that's beside the point.
Okay, I'm sorry. Yeah, but so first thing that I was working on was extended engineering testing. Thank you to William Gomeringer for giving us access to this huge machine. So what I was in charge of was basically using stuff created by Larry to test the page reclamation algorithm over large systems. So the system we were given access to had 896 CPUs and 24 terabytes worth of memory, or 25 terabytes worth of memory. And all that would happen would basically first we would fill up the page cache and then spawn a bunch of processes to eat up the memory and make sure that all the memory that was previously eaten up could be deleted and reclaimed by these new processes. And then a slightly more intense test was to create all of this, also fill out the page cache, then create all these processes to try to eat up the memory, but also run in the background other processes that are trying to read and write to these created files to make it more difficult for the algorithm to figure out when and what to delete.
Hey, Ryan. Are you intending to be sharing something?
Oh, yeah, I thought I was presenting.
I was going to say I couldn't see anything either, but...
Oh, goodness. Okay.
It was very clear, so I wasn't entirely sure. So...
Oh, so sorry. Can you guys see? I'm so sorry.
Don't worry.
And it's... Okay. Yep, I forgot to click allow, so that's on me.
Stupid security.
Completely on me. Okay. And it says I cannot share my screen. This is incredible.
Langdon, you might have to give him permission to do that, right?
I was just looking at that. I don't know that I'm cool enough.
Remember this? Oh, yep. Allow. Okay, can you guys see what I'm seeing now?
Yeah.
It's loading, but yes.
Okay. Brilliant.
Awesome.
Now we have Inception.
Okay.
Oh, much better.
Okay. Can everyone see what I'm seeing? Should have
Yes.
checked that first. Okay. so
Beautiful.
From the top. Yes, thank you again to William Gomeringer for access to the system. So yeah, basically what I just said. I was in charge of running a few tests to make sure that the Linux page reclamation algorithm worked on large scale. And I said before, the system I was testing had 896 CPUs and 25 terabytes worth of memory. So the initial test that Larry gave me was to fill up the page cache and then spawn up multiple processes, about one per CPU, that would eat up roughly 28 gigs of memory and make sure that the algorithm could handle deleting and reassigning these bits of memory. And then a slightly more intense test that we came up with was to just expand upon the prior, where once this memory was created and we spawned the processes to eat up and reclaim the memory, other processes would be assigned to read to this previously made bits of memory, just to make it so it would stay in the active pool rather than move to the inactive and reference pool. So that was my first little project, and currently I am working on a bandwidth limiter organized by Peter Portante and working with Jesper Brewer, Andrea Arcanelli, Larry, Toke Jorgensen, WebScales, David Budenhof, Leonard Pottering. All these guys have been an extreme help, especially to get started. And the current way the project is going is we intend to create a BPF hook wherein we can attach BPF filters onto the write system call. It may later be expanded to include the read system call as well. And then once this hook has been created, we will create a bandwidth limiter in eBPF. This has been done before. What I've looked into has been the NetCount program, which WebScales sent to me, and that seems to be all that we really need. And once it's been implemented, people will be able to assign bandwidth limits on a file descriptor basis, and this is supposed to help combat the issue wherein if you have multiple containers and they all attempt to write to either standard out or standard error, too high a bandwidth can cause the entire system to lock up and crash. So this is just going to be implementing certain policies wherein if too high a bandwidth is sent to standard out, it might be blocked and then later written or dropped completely, depending on what the user defines they would like to happen for that said file descriptor. But yeah, that is a really brief description of what I've been currently working on. If anybody has any questions, I can take them now, or my email is rysulliv@redhat.com. If you would like, I can send you some documents as well.
Very good.
Thank you.
Thanks for that. And then I think you're actually doing another project update?
Currently, I'm just working on these two.
Okay.
He was just
Sorry, I was
very efficiently putting them in the same presentation.
right. Okay.
These were just the
Sometimes
two
when we talk about the kind of acronyms in the abstract, it gets a little bit unclear whether this is like a separate thing or together or.
Oh yeah. These
sorry,
are two separate things.
Yep, two separate projects. Yeah, we had one other fellow working with him, but we're trying to. His visa status expired, and we're trying to get him back so he gets.
Yeah,
some
we're
help.
trying to get.
Together. They'll work well together.
That whole legality thing.
Was the first project finished, Ryan, or was that one just starting to?
That's winding down right now. So we have to give access back to Mr. Gomeringer. So I will only be able to access it probably until the end of this week. So I have been able to play around with it, but the main bulk of the testing has been mainly finished.
So is the algorithm mostly working, or?
Yes. Yeah.
You didn't find any horrible
yeah, I didn't have any trouble. I didn't have any troubles with it when I was testing. So the only real thing was just how long it took. So I would basically just run it and then leave it and then work on the bandwidth limiter in the meantime. But I didn't have any issues with it. So for right now, I have no bad news to report, which I guess is good news.
So just a couple of words on this, or sentences. The origin of this project is way back. This is the type of problems. This is the type of workload that caused the Linux kernel to hang or whatever under really heavy loads because of spin lock resolution and spin lock granularity. So over time, I actually changed and fixed this stuff, but we test it every single time we get a larger and larger piece of hardware. We test it. So what we had Ryan do is start to automate the test procedures. So eventually, we don't have to have a human do it anymore. We'll have some AI ML application test and verify that the most stressful pieces of locking code inside the kernel work correctly. So, and this will all sort of funnel into the work that Parul is working on too, a memory bandwidth work that she's doing. So eventually Ryan will probably help her too. So anyways, that's all. Sorry.
So does Ryan hold the record for doing the largest page memory testing ever at Red Hat?
No, this is actually a fairly small system in retrospect.
Darn.
We have had a 64 terabyte system. This one's only 4. It's the number of NUMA nodes that is outside of the norm in this thing. This thing has what did it have, 16 or 32 nodes? I've forgotten.
I thought it was 16.
16. So for that amount of memory, usually you have a larger number of NUMA nodes. With a smaller number of NUMA nodes, it puts more stress on the spin locks. So that's why we had to test it.
Got it. Cool.
So.
All right. Just jumping in. So we would love follow-up questions. Maybe we'll have time at the end, but we do want to move on so we can get to Ahmed. Thank you for that presentation. And Ahmed, do you want to kind of take it away?
Yeah, thank you, Langdon. Let me share my screen here. All right. Let me. So, welcome to the last pilot session of the paper reading group. In the first couple of sessions, we had a look at the value that research papers provide, both to folks who are experts of a field, as well as folks who are interested in finding out more about it. And then we also looked at indicators of flags that tell us if a paper is worth reading. Spend 5 minutes figuring out if it's worth spending 5 hours taking apart and understanding. In the last session, we're going to wrap up this discussion with analysis of research papers themselves. And normally the way that this discussion session happens is somebody reads a paper, they give a 20-minute talk about that paper, and then everyone discusses the technical aspects of it. But what that ends up doing is getting really technically difficult to follow for someone who's not an expert of the field. And that is one of the challenges that we're trying to address if we do this paper reading session, is to have something that's, and everyone can get involved in. There's something for everyone in there so that they can feel comfortable joining in and taking part in the discussions. Now, there is wisdom in the conventional approach. Yes, there are certain papers that do merit a full hour or maybe even 2 sessions of discussion, but we can also have a new type of session that runs in tandem with us. And that session, instead of doing a depth-first exploration, could potentially do a breadth-first exploration where we're not really interested in too much technical depth, but rather just trying to get an understanding of where the field stands today. And so we're going to do this experiment because, what a better place to do it than a pilot session. So this particular session is split into 4 parts. In the first part, we're just going to list some papers that we'll discuss. Now, there was some homework. If somebody had read a paper on deep learning for self-driving autonomous cars, then they would have discussed it here. If you have done that, great. We'll get to how we can share that in a bit, but if you haven't, that's okay, I've got you covered. So the first, we're going to list out the papers. Then we're going to just talk about the challenges in those papers. Not going to talk about how they're solving them, just what is it that these papers are trying to address, and that's usually just the introduction section. Then we're going to get to solutions. What are the solutions being proposed? And here's where this gets interesting. Sometimes a paper might propose a solution for one challenge, but now that we've seen the different challenges, we might see that one solution applies to a different challenge in a different paper. So there's some nice things that can come out of this breadth first exploration. And then finally, once we've done a very high level overview of proposed solutions, say 2-3 minutes per solution, then we can talk about at a very high level, what are the limitations of the proposed solution, how effective it really is. So if you've read a paper you want to share, please put the name of the paper and the link in the chat. If you haven't, that's okay. I've got 2 or 3 papers here, and I'll just fill in this table. But if you have, please do put it. So let's give it about 30-40 seconds while I copy it in myself. And we have no takers. That's fine. What I'll do is I'll put the links in the chat as well, just because copying them off the screen is going to be hard. So here are the papers that I'll be talking about. And this is going to be very brief. I'm not going to dive into too much detail into any of these. So, all right, so let's just, due to lack of time, we'll just skip ahead and let's start with the first part. What are the challenges? Now, you can open up the paper. Yeah, it's not a pop quiz, don't worry. No questions. So if you open the first paper, or it's basically a paper about object detection. So if you're driving and there's an object on the road, and if it's a self-driving car, it wants to avoid that object. The way that it's currently done is very similar to how people do it, and that is we use stereo vision. You know, our left eye sees an image, our right eye sees an image, and our brain puts it together, uses geometric cues, to figure out what's the 3D location of that object. And that tells us if it's an object, how close it is, and how we should avoid that. Now, the limitation for that is that this stereo vision property, which you can do with cameras, is that it only works if you have an optimal sized object within an optimal distance. But you know, when you're driving, you have to expect the unexpected. So this technique of just using geometric cues isn't really that effective. So that's the first challenge. How do we figure out that there's an object on the road by using something other than geometric cues? The second paper was, for me, the most interesting one. This one talks about future prediction. So when you're driving on the road, as a human being, you have very long reaction times. You're very poor at reacting to something. And that's okay. It applies to everyone. It's a global thing. Machines, on the other hand, are quite fast. They can respond very quickly and very precisely. But what humans are able to do, the machines cannot, is future perception. You can look at a scene and you can anticipate how that scene will evolve in the future. Sorry. Yeah. You can anticipate how that scene will evolve in the future, and then you can proactively do something. So if you're seeing a pedestrian walk towards crossing, and they have the right of way, you can start to slow down. Because you know that may cross, they may not cross. But in case they do try to cross, you would have slowed down enough, you can stop within a reasonable distance. Whereas a machine will not be able to tell that. It will only know that the pedestrian is trying to cross once the pedestrian enters the crossing. And by that time, it might be too late for the machine, even if it reacts instantly, to stop the vehicle. So that's the second problem that you're trying to tackle. How do you tell a machine, how do you train a machine figure out that something's going to happen in the future? The third one was a little different from the first two. That one was just simply saying that, we need test beds to test autonomous driving algorithms. We can't use a real car for very, very obvious reasons. You don't want to just crash that into something because your algorithm was missing some variables. So what do? Well, you want something that's low cost, and you want something that's not a simulation, because we have good simulators, but they're still idealistic environments. So you want something real, a scaled out version perhaps. And that's what this paper tries to build, a low cost, scaled testbed for self-driving cars, but something that's capable of running real workload. So I'm going to put that in there as well, the third paper and the third challenge. So let's just leave it there and let's move on to the next part, which is the proposed solutions. So you know what, I will take a pop this here. So you've given me the idea. I wasn't planning to. So let me ask the attendees. As a human being, you perceive depth through stereo vision. What other way do you perceive depth?
Sound.
True. Yes. What else?
Time.
There's something even more simple. So if you cover one of your eyes, can you still see the depth of the objects in front of you?
No.
Yes, you can. It's the appearance of things. If you cover your eye and one object is blocking another object, then you know that the object that you can see is closer to you and the object that's getting blocked is further away. And that's the exact principle that they're utilizing. Well, you can partially see. So that's the principle that they utilize, that you can have your stereo vision giving you a probability graph of what be in your path, but then you can also take one of the images, you can run it through a convolutional neural net, and you can generate a second probability graph that's based on just appearance and looking for spatial cues, and then you can fuse these two probability graphs together. And when you fuse two probabilities, what do you use? Bayesian filtering. That's exactly what they are using. And they have shown that gives you significant improvements in not only detecting obstacles, but also eliminating false positives. So that's the first one. Second challenge was for paper 2, which was how do you perceive something in the future? Now, this one was purely, as we have seen, a paper about convolutional neural nets. Because this we saw in the first one. If you have an image, what do? You set up a convolutional neural net, because that will give you a lot of information and all contextual information. So what they're trying to do is just use a convolutional neural net to look at the environment and then predict what's going to happen at time t is equal to 0, 1, 2, 3, with a resolution that you can adjust. Of course, the longer you try to look, the worse the result. So it will be up to a certain limit with a certain time step. So the two challenges that they had, one, what is your inputs going to be? Because machine learning models like consistent input. If you have one car that has 4 sensors, another car that has 6 sensors, you won't be able to use the same model for both of them. So you want a consistent image. So what they generate is something that they're calling a dynamic occupancy grid map, or DOGMA. I think this is figure 1 in the paper if you have it open. A DOGMA is like a bird's eye view of the environment that's generated by fusing sensor data. Each pixel in that image is not color. It is actually a probability of whether this pixel is occupied by something and the probability that this pixel is moving with a velocity in the north and the west directions. And that's the information that your model can then take and then analyze and then predict what's going to happen next. And what is it predicting? It's predicting what's going to happen to the static object. And what's going to happen to it? Nothing. Static objects are not moving. But What about all the dynamic objects that are moving, pedestrians, cars? For each time step that you're interested in, let's say you have a time step of 100 milliseconds. So for each 100 millisecond in the future, you will generate a new graph or a new map that shows what the new locations and velocities of all these objects that are moving will be, and the probabilities associated with them. And how do you then train something like this? You need a bunch of training data, because something I should have pointed out, both the first challenge and the second challenge, they're both being solved by supervised learning. And supervised learning needs training data. How do you get it? Well, you don't really have any data sets that are too specific to what they're trying to do. So they just write their own classifier. They record a bunch of videos. They write their own classifier that will classify objects or outputs, static or dynamic with all the probability maps. And that's what they use to train, which was really, really nice, because that's something that most people who try to do supervised learning end up struggling with, where they train their model with a certain data set, and if something new comes along, they're not really prepared. So there's never enough training data to train for corner cases or infrequent scenarios. Let me just paste that in there. Oh, well, that's not good. Right, better. Right, and then the last one was the simplest one. The third challenge was making a low-cost scaled testbed. What they did here was, again, supervised learning, because they were actually trying to copy the NVIDIA Dave 2 testbed. What they used was a scale of 1 to 24 ratio RC car, and they used a Raspberry Pi 3. And what they were able to demonstrate was that you can actually run that real-world convolutional neural net that NVIDIA used using TensorFlow on a Raspberry Pi. I mean, it had its limitations, but in terms of how continuous the steering was, but overall, they were able to achieve 40 commands executed per second versus NVIDIA's 30 commands per second. Now, there's a red flag in there somewhere. If a Raspberry Pi is doing 40 commands and NVIDIA with its massive GPUs is only doing 30, something is off. What that is, I will leave it up to you as an exercise if you're interested. Why is it they're doing 40 hertz and NVIDIA is doing 30? But the main thing that I want to point out here is that at this point, we've looked at the solutions. We have not got into a lot of technical depth. We've just looked at what are the challenges in the field and just a very high-level overview of how people have gone about solving them. And the point of this exercise is that even if you're not an expert of the field, even if you know just the basics of machine learning, or basics of self-driving cars, or even the basics of mathematics, then all of this would start to make a lot more sense than if you were just deep diving into all the differential equations and the learning equations and the Bayesian filter equations that were given in these papers. In the interest of time, I'll skip the last one. I'll just say the biggest limitation in all the three things that we saw there was it's all supervised learning, whereas I believe that self-driving cars should be reinforcement learning. They're using a 200 by 64 pixel image. They're claiming it's exactly the amount that NVIDIA uses. But that could be definitely it, Mike. Mike is saying that the size of the image might be lower for the Raspberry Pi. So so they're using supervised learning, which will always struggle from the lack of data. Whereas if you have reinforcement learning, not only you're mostly more equipped to handle things because you're going to get the ability to evolve over time and to learn over time. You can get your actions and then rewards and then actions based on that. So so they're not using floating point unit. It could be. I mean, they've only said they're using the same dimension of the convolutional neural net that NVIDIA used, but it could be that it's the data type that's a little reduced. So thank you so much for being part of these 3 pilot sessions. As a reminder, if you're interested in this sort of thing happening on a regular basis and with its own time slot, then let us know. Use the QR code or the form link to sign up. And then based on the number of people who are interested, we will talk about offline, what kind of session we want to do, when do we want to do this, how frequently, and how do you want to structure the different topics so that everyone is interested and involved. So with that, I think that's my talk. Thank you so much. And I will hand it back over to Langdon.
Thanks. I'm a little disappointed that you haven't embedded the Red Hat logo in the center of your QR code, because that's what makes QR codes fun, is you can put pictures in them. So yeah, thanks so much. Please do sign up. Let Ahmed know if this is something that you'd like to continue, if you'd like to participate. I think we would very much like to see kind of more like kind of university involvement in something like that. Particularly if you're more new to the field, etc. So please do. The last thing on our agenda, unless anybody had any questions before we kind of move on. There's very little video on, so I can't see anybody going, oh, wait. But all right, so we'll move on. I'm going to throw Bandhan likely under the bus. Could you just put the link maybe directly in the chat, just in case anybody missed it? Bandhan from his new digs in, I don't know, somewhere not Boston, Massachusetts. I think he's looking for sound.
Yeah, can you hear me now?
Yeah.
So just want to confirm. So I'm talking about the EIRs.
Yeah.
Right?
Right. So the idea is I'm emceeing, so I'll make him pitch, but I can also answer questions. So Bandhan, you want to explain a little bit about what the EIR is, for example, the expansion of the acronym, and why someone might want to do it, and that would be cool.
Yeah. So EIR, the EIR program, as of today, I think I don't think we have it with any other universities. But the one that we are talking about today is for Boston University, and it stands for Engineer in Residence program. And so what typically it entails is you as a Red Hat engineer, try to think of things that you usually don't think about maybe on your day-to-day work. So in a nutshell, what you're trying to do is you're trying to work with students on a variety of topics, and these could range from projects that either they are helpful for the students in one way or the other, or they might be even projects that you propose to the students, and they could help them in their career, or maybe even decide what career they are trying to choose. That's part of it. There's other things that you could do as an engineer in residence. You could spend some time, just like me and Langdon do, teaching classes. These classes are a little bit different from the typical classes that you could think of as students go to, in the sense that they are more kind of designed to help the students get up to speed when they're ready to go to the industry, or attend their first interview. And besides for these two things, you could also, the program is pretty flexible. All it entails is you as an engineer spending some time with students from the university, maybe giving them career advice, or maybe even help them decide on what would be a good career based on the projects they have done, or maybe even their interests. So from the perspective of someone who has been had, or maybe in the past year I don't know how long I have been an EIR, but because I think my page still shows, maybe even Langdon's page shows that he's also an EIR. But I think when it was pretty new to me, the things that I kind of thought were different was what I just started this introduction of how I introduced this program, right? I mean, I think the way to think about the EIR program is you are not typically thinking of a project as something that ends up being a real product or something that ends up at the hands of a customer. You try to switch gears a little bit and think of things that are interesting in general, and or maybe help a student, or maybe even you think of the project as something where you learn something and also you help a student learn something new. So so that's I would say is a very like a short introduction to what you would do as an EIR. If you are a full-time, I think the requirements for the EIR program is you are a full-time employee at Red Hat, and so that probably rules out interns, but I'm not sure. Langdon might clear that out. But if you are a full-time employee and you are interested in spending some of your time, your manager is okay with it, and you would like to spend some time working with students, helping them in their career, teaching classes, or maybe working on some projects that are outside of your regular work routine, then this is the perfect thing to do. So, and have I missed something, Langdon?
No, that was pretty good. Definitely not something you'd want to risk while doing kind of an internship or even part-time. It's kind of hard. However, managers have been encouraged with the Boston office in particular, but the Westford office as well, to support doing this kind of stuff, with their employees. It's a great, it's what's really, at least for me, what's really interesting about it, right? I've been doing this for quite a long time now. I won't entirely date myself. It's less than Larry. How's that? But it's really interesting, and I think it has been for all of us who've been connected to it, to reconnect with students and understand kind of where basically the changes in kind of learning computer science or learning how to work with computers and stuff, like how that's so different than when I went to college, as well as what's important to students and to kind of recent graduates, that kind of stuff, or even early grad students. But then even getting into PhD work is like, where are they finding interesting things, which I think really brings some perspective to the stuff we do all the time. So I think that's been really interesting. I also, like me personally, I've done a lot of startups over the years, and working with students who have some massive startup idea, I think is really interesting and a lot of fun, even kind of no matter how out there the startup is. One of the ones I think has been doing really, really well is a startup to help you measure like your recipe, in a sense, for making espresso, and how seriously people take that, and how they can actually run a whole business around it, which I think is really kind of amazing. Also using AI in the mix there. So it's really quite interesting. It can kind of be a few hours a week, up to, generally speaking, I would say most people spend less than a day a week. But we can try to figure out what matches to you. Do keep in mind that if you do live in the Westford area or something, being physically on campus once kind of pandemic fears are over with, is kind of important. Not only from because if you're not present there, the students won't connect with you. They're not gonna. It's think about the phenomenon of when you might have been in school or whatever. It's a big deal to go knock on somebody's door, like their office or something, and even for office hours. Imagine trying to reach out to somebody on the phone, right, or email or whatever, sight unseen. So it's really, really important that you be physically present, even if you're doing other stuff, so that they get to know your face and recognize you as approachable, that kind of thing. And they have snacks, and they're different snacks from the Red Hat snacks, so that should be appealing. So that's our little pitch. As I think Sarah said in the chat, I didn't have it open, but yeah, definitely reach out to Sarah, and she can help coordinate. And whereas, like, you know, Bandhan and I, you know, and others actually can share our experience and help you come up with what might be a good plan. But I think that is the end of our agenda. Does anybody have anything else that they want